In this video, we're going to take a look at reaction mechanisms and how we can use them to figure out the rate law. So a reaction mechanism is really just the path that your reactants are going to take to turn into products. They might have one step in changing from reactants to products. It might happen all in one step. Or it might happen in many steps, two or more, multi-step. And this is called the reaction mechanism, the pathway taken. So if you have a reaction that occurs all in a single step, we call that an elementary reaction. So be on the lookout for problems. If you see the word elementary, it means the reaction happens all in a single step, and there's actually a really great shortcut we can use to find the rate law if this is the case. So if you remember, this basically entire chapter, I've been saying that in order to determine the orders of the reactants and the rate laws, you have to use experimental data. They have to be determined experimentally, and you can't just look at the reaction coefficients to determine them. Why this is because there's usually a series of steps happening at different rates, and you can't use the coefficients because that's just showing what's happening in the overall reaction, not the different steps. However, if you know a reaction is elementary and it happens all in one step, then you can actually use the coefficients, also called the molecularity, to determine the orders. If you remember the other ways that we looked at to find the the reaction orders, one way was doing the method of initial rates, where we gave you initial concentrations of each reactant, the initial rate, and you see how they each change and their impact on the rate. That was one experimental way. The other way was making graphs of concentration versus time, natural log of concentration versus time, 1 over concentration versus time. We can do it graphically, but again, using experimental data to determine the orders. However, as I just said, if you know the reaction is elementary, then you can purely use the stoichiometry of the reaction to fill in your reaction orders. So what I mean by that is if you have a unimolecular process, unimolecular meaning one molecule reacting, overall you're going to have a first order rate law. So if you look at this has one reactant. The rate law for this would be rate on the left equals K, and I would just put my reactant and raise it to the power that is the coefficient. I can do that because this is an elementary process. This is happening all in one step. So it kind of makes sense that I just need one A molecule to react in a step and turn into products. And that's why I can just make the coefficients become the orders. I'm only having the reactants, so it doesn't matter what the products are here. Only the reactants raised to the power that is their coefficient, and only if it says elementary. If you have a bimolecular process, bimolecular means two molecules are reacting. Overall, it's going to be second order. So two different scenarios you might see. You might see two different reactants. Take a moment, write what the rate law would be if this is an elementary process. So if I see the word elementary or happening all in one step, I just simply take the coefficients and turn them into orders. So rate equals K, coefficient of A is 1, so A to the first power, B to the second power, or B to the first power, sorry, each have orders of 1. And notice it's overall second order, 1, 2. 1 plus 1 is 2. So it kind of makes sense that if you have two reactants colliding, they would equally impact the rate. If I only have one reactant to start with in just one step, it would be directly proportional to the rate. The more reactant A, the faster the rate. The less reactant A, the slower the rate, in a directly proportional relationship. And the same thing here. So these relationships work out where the coefficients become the orders only if it is an elementary reaction. And here I have two A's, so again it's bimolecular, two reactant molecules. And if I'm writing the rate law, B rate equals K, A, raise it to the power that is the coefficient, A squared. Notice both of these are overall second order because there are two molecules reacting. It makes sense that if I were to double A, since I need two A's to collide, it would end up quadrupling the rate because the rate is proportional to A squared. So this is just showing these kind of different relationships, but spanning into having three molecules reacting all in one step. Here's three A's. The rate would be Ka cubed because the coefficient of A would be 3. This is two A's and one B, so Ka squared B. And this is ABC, three different ABC, each having power or order of 1 because those are the coefficients. Again, you can only do this where the stoichiometry can be used to determine the rate law if it happens all in one step. So look out for that word elementary or all in one step. Notice that the coefficients just become the orders. So let's take a moment though and think about how likely it is for a reaction to happen all in one step. Now, if you have a unimolecular reaction, you just have one reactant molecule. Okay, it's likely that that might happen all in one step. It's possible. 2. All right, maybe that's likely. Think about, in order to react, we have this thing called collision theory where both molecules have to, if you're dealing with 2, the molecules have to have enough energy to overcome the activation energy, and you need to have the right orientation. So those 2 factors have to be met. So let's start talking about a termolecular reaction. Termolecular meaning 3 molecules reacting. Is it likely that this is all going to occur in one step? That these 3 molecules are each going to come together with the right amount of energy in the right orientation so the correct bonds are formed and broken to have a successful reaction? No, that is very statistically improbable for that to happen. It's likely that even if they do collide, it's not going to be an effective collision. And again, if you didn't watch that intro video, that's where we talk about effective collisions and those 2 factors, energy and orientation. These would likely end up being multi-step reactions. So if you see a reaction that has 3 or more molecules reacting, it's likely not going to happen all in one step. It's likely you're going to have multi-steps, with each step being maybe unimolecular or bimolecular, because it's a lot more likely for 1 or 2 molecules to have to collide than 3 with the perfect energy and orientation. So let's talk about multi-step reactions. If a reaction goes through a multi-step reaction, we are assuming each step is an elementary reaction, meaning each step occurs all in one step. You might see these things called intermediates. Intermediates are substances that are formed in one step and used up later on, so it never actually appears in the overall reaction. In this multi-step mechanism, there's a couple of requirements. The sum of all the steps, each of which is an elementary step, must add up to the overall reaction. And once you determine the mechanism must agree with the experimentally determined rate law. So once you come up with a good mechanism, it does still have to be verified with an experiment. Therefore, that's why we can do this, where if we know something happens all in one step, we can make the coefficients become orders because it actually is based on experiment. Okay, so let's look at a possible multi-step mechanism. So here's one. Notice this has 2 steps. If you're given the steps, let's practice getting the overall reaction. Take a moment, pause the video, and then check your work. So if I'm adding these up, I'm going to add up everything on the left, everything on the right, and you might see things cancel. So you'll notice that I see NO3 on both sides. It's made in this step and used up later. Do you remember what we call that? We call that an intermediate. It's not going to appear in the overall reaction. You'll also notice that NO2 is, there's 2 on this side, but 1 on this side. So one of them is going to end up canceling. NO2 still appears in the overall reaction. That is not an intermediate. An intermediate is not in the overall, and it's made and then used up. These just end up canceling because I've got 2 on the left and 1 on the right. And now I can kind of add up everything that's there. So NO2 plus CO remain on the left. I don't care which order it's in. I've got NO and CO2 on the right. And as I said, NO3 is an intermediate. It's made and then used up. So let's say a question asks you, here are the steps, write the rate law for the overall reaction. And notice I put here which step is fast and which step is slow. What do you think the rate law is going to depend on? Which step? So notice that each step occurs at different rates, and that information should be given in the problem. In a multi-step, the rate of the overall is going to depend on the slow step. The slow step is going to limit how fast the reaction can go. So if you think about it, this step is going slow, this step is going fast. Even if this step goes 3 times as fast as that one, I can't go any faster until I get the results from that, or the products from that first reaction. So it's always the slow step that limits your rate law. We call that the rate determining step, or sometimes the rate limiting step. And this is what's going to give us the rate law for the overall reaction. So even though I wrote the overall reaction here, and even though the question is asking me for the rate law for the overall reaction, I'm going to my slow step and that is what I'm going to take my rate law from. So for this one, here's my slow step. It happens all in one step, so I can just take the coefficients and turn them into orders. So my rate equals K. There's 2 NO2, so that's the same as 2 NO2, NO2 squared. Yes, one of the NO2s canceled to get to the overall, but in this first step that is slow, I still have 2 NO2s, so that's what should appear in my rate law. So notice my rate law does not match my overall reaction, because that's not what's happening all in one step. It's matching my slow step. Always, 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 you're looking at your slow step to determine the rate law. This suggests that even though CO is in my overall reaction, it's the other reactant, notice it's not in my rate law. So that means that the rate does not depend on CO at all. Yes, it has to be there, but adding more is not going to make the rate go faster because it's zero order with respect to CO. So all those problems we've done in the past where you found something is zero order with respect to that reactant, and you might have wondered, well, how could it be zero order? It's a reactant, it has to be there. The reason is it wasn't in the slow step. CO is in my fast step. So adding more is not going to make the slow step go any faster, and it's not going to make my rate go any faster. Take a moment, try this example, then check your work. So in this one, I have my slow step, I have my fast step. It asks me write the equation for the overall reaction, so I'm just adding these two together. Notice that these O's cancel, and they're called intermediates. And I get 2 N2Os on the left, I've got 2 N2s and an O2 on the right. If these steps do not add up to my overall that they're asking about, then this could not be a possible mechanism. Next is write the rate law. So even though they're asking for the overall, I'm looking at my slow step. That's what's going to limit the reaction. And all I'm going to do, here's my slow step, make it into the rate law by taking the coefficients of just the reactant. The product doesn't appear there, K, N2O. Simple. So that was with the slow step that was initial. Let's look at if the slow step comes later on. So let's consider this example. Here we've got termolecular 2 plus 1. There's 3 molecules reacting. I'm telling you this is the rate law. And my question is this reaction likely to occur in a single step? No, we just said it's very unlikely for 3 molecules to come together in the right orientation with the right energy for a successful collision. So let's look at a different mechanism. Let's consider these 2 steps. My first step is fast. These double arrows mean equilibrium, meaning it's going just as fast forward as in reverse. The forward and reverse reaction are happening at technically the same speeds. And I'm giving 2 different Ks, constant, rate constant, 1 forward, 1 reverse. And then this step is my slow step. So notice that the rate of the overall action is going to depend on the slow step, which in this case is step 2. If I was going to write the rate law for the overall reaction, I'm just looking at the slow step, that would be rate equals K, NOBR2 times NO. There's a slight problem that happens. What is NOBR2? It's made in this step, it's used up later. It actually is an intermediate, and it's very, very difficult to measure the concentration of an intermediate because it's made and then used. It's very temporary species. It has an uncertain or an unknown concentrations. And we want to make sure we express our rate law in terms of reactants, sometimes also in terms of catalysts, but not really in terms of intermediates. Are there a few exceptions where this might happen? There are maybe a few, but for the most part, we don't want an intermediate. We want our reactants, which in this case is NO and Br2. So how can we manipulate this so that we replace the intermediate with our reactants? I'm going to show you a derivation, and then I'm going to show you a shortcut. So the derivation is that, notice that this is equilibrium, and that means that my forward rate is equal to my reverse rate. Well, if I plug in terms of rate, instead of rate, the rate laws, going forward, this happens all in one step, so I can take the coefficients and turn them into orders. The rate law going forward is K, NO to the first, Br2 to the first. The rate law going in reverse is, now I'm going to use this K, NOBr2 raised to the first. Move this out of the way for you. Okay, I'm going to rearrange this, and I'm just going to solve for NOBr2. So I'm going to divide both sides by k minus 1, which is just the reverse rate constant. And now I see I have NOBr2 in terms of the reactants. I've gotten that from my first step. And now I can plug this in to my rate law for the slow step, which is what we said we want to base our the slow step, which is what we said I want to base my entire reaction on. So the rate law of the slow step we said was K NOBr2 NO. So I'm just going to take this and plug in place of NOBr2. And I have this bunch of K's, but a constant times a constant divided by a constant is still a constant. So I'm just going to make that K. NO squared, because there's two NOs, Br2. So in general, when a fast step precedes a slow one, we can solve for the concentration of the intermediate by assuming an equilibrium is established and doing what I just did, where you're setting the forward and reverse rate laws in that first step equal to each other. Now, if I'm doing this quickly in a context of a problem, this is how I typically look at it without doing this long derivation. I go to my slow step. I write my rate law based on the coefficients. So rate equals K, NOBr2 to the first power, NO to the first power. Oh, wait a minute. And then I say, uh-oh, there's an intermediate. So be on the lookout if you wrote an intermediate. NOBr2 gets canceled out. It's not in my overall reaction. I don't want it there. So all I do is I go up and I say, let me find that intermediate where it's first made. And let me see what made it. Oh, NO plus Br2 made NOBr2. So let me just take NO and Br2 and replace that, put that in the place of NOBr2. Because let's plug these in instead of that, since that's what's making it. So boom, there I did it, and now I can combine like terms, NO, and make it NO squared, and there's exactly what I did before. Take a moment, try this example, and then pause it and check your work. So I'm just going to do it the way I did before. So here I am writing the rate law of my slow step. Even though they asked me for the overall, I'm not using the overall. I'm using the slow step and only the reactants raised to the power. There's a coefficient. Don't forget rate equals K. And I say, uh-oh, this is an intermediate. Let me find where it's made. Oh, there it is. It's made over here. What made it? Oh, these two guys made it. So let's plug these in instead. And I get, sorry, I have to keep moving this, NO times NO, which is NO squared, Br2. And there's my rate law. So this was hopefully helping you to figure out mechanisms. Again, if it occurs all in one step, the reactants, the coefficients of the reactants just become their orders. Don't put the products in. If it happens in multi-steps, all you're doing is the slow step. It gives you the overall order. And if the slow step is first, it's an easy plug and chug. If the slow step is second and you have an intermediate, you got to go back up to the first step it's made and plug in the reactants instead.